Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can evaluate logarithms if they don't go in perfectly. So, for example, when we were talking about evaluating logarithms in our previous video, we reminded ourselves that logarithms are repeated division, meaning I'm going to take the number that I put in and divide it by our base and ask myself, how many times do I have to do that until I get to 1? So, for example, with this one, we've got the number 64, and we can rewrite it as an exponential saying 4 to what power equals 64, because essentially I'm trying to do the opposite. I'm telling myself, how many times do I need to divide 64 by 4 until I get to the number 1? And so in this case, we can see 64 divided by 4 is 16, 16 divided by 4 is 4, and 4 divided by 4 is 1. So that means that how many times do I need to multiply 4 to get 64? Well, 4 to the power of 3 is 64, or the log base 4 of 64 is equal to 3, because it takes me 3 times to divide 64 by 4 to get 1. And that worked out beautifully. It came out even. But what if we had a question like this one? So this one is log base 10 of 20, meaning I'm asking myself, how many times do I need to divide 20 by 10 in order to get to the number 1? Well, 20 divided by 10 is 2. And if I take 2 and divide it by 10, then all of a sudden I get to 0.2. So I know that all of a sudden here, what we're running into is this problem where it definitely takes 1 full division, but it doesn't take a full second one. I know it's going to be a division somewhere between 1 and 2. Now, how do I figure that out? Well, there are a couple of different resources that we can look at. We're going to look at one in this video, and then in the next video, we're going to talk about something called change of base. But one thing that we can do is our calculators actually have some common bases that they will just calculate it out for us. So if it's not something that we can do using that repeated division, or something we don't want to do using that repeated division, we can actually use these common logarithms that are in our calculator. Now, there are 2 in our calculator that are common. There's the log base of 10, and the reason why 10 is common is because 10 is the base that we count in. So our numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice how there are 10 digits there. After we get to 9, we go back to 0 in the sense that we go to 10, where the 1's digit is a 0. And then we go all the way up to 19 and repeat back to 20, where our 1's digit is a 0 again. So we're in this base of 10. Because that's how we do our math here in the world, what we have is all of our calculators default to a base of 10. So on your calculator, if you see the button that says log, that is not referring to any logarithm, but that's referring to a logarithm of base 10. And what we can do is we can actually figure out what log base 10 of 12 is using that button. So what we can do is we can just type in the option of log of 12, and it'll evaluate it for us. And so as we do that, if I do the log of 12, I end up getting something like 1.08. And that's rounded. This is going to go on forever. But it's telling me that to go from 12 and get it down to 1, how many times do I need to divide it by 10? Well, I need to divide it by 10 once, and then a little bit more, but I don't want to divide it a whole nother time. So that's kind of what we're looking at here. And that's our log button. Now, the other common logarithm that we talk about is when we have a log base of e. And what we actually call a log base of e is we actually call it a natural log. And the reason why is as we explored the idea of the number e, which is 2.71, going on forever, kind of like how pi goes on forever. But this idea that when it comes to how things grow exponentially in nature, ultimately, if we were to compound continuously or look at reevaluating something all the time, that rate at which we reevaluate at of interest, the rate at which we grow, is going to be equal to that e. So that's what happens in nature. Therefore, we call this the natural log, because we're saying this is how it works in nature as we look at it. And that natural log is represented by ln, because we still want it to be a log, so we want it to start with an L, but it's the natural log, so we're going to say ln instead of nl. Got it? And so what we can do is we can also evaluate that one there. Now, our natural log button is typically near our log button. On a TI-84 calculator, it's right below it. And we can do that natural log of 0.75, asking myself, how many times do I need to multiply 0.75, or how many times do I need to divide 3/4 or 0.75 by e until I get to 1? Well, according to our calculator, the answer is negative not 0, negative 0.29-ish rounded. So that means we need to put it to a negative almost 1/3 power. Interesting, right? But that's how we can do it. And it makes it so easy to just type it into our calculator and have it spout that out. So let's take a look at a couple of examples here of how we can use that common log. So we can type it right in so we can see the logarithm of 17 is referring to log base 10 of 17, and that's going to be equal to 1.23. Our log of 7/10 is going to be equal to negative 0.15, and you can choose how many decimal places to round this to. I'm rounding to the hundredths place or 2 decimal places, but we can kind of look at it that way. What happens if we do that natural log? You can see that those are a little bit different. So the natural log of 1.2 is going to be 0.182. The natural log of 15 is going to be 2.71, basically. Ironically, it's pretty close to E. Things like that. Now, what happens if we try to use this button and a negative? So look at what happens if we do the logarithm of -1. Notice how it says error, no real answers. Things like that on our calculators. It doesn't want to work. The reason why is, remember what a logarithm is. It's repeated division. So if I have something like -1 and I want to know how many times I divide that by my base of 10 to get the answer of 1, well, what is a negative divided by a positive? It's always going to be a negative. And it's impossible for that negative to turn into a positive unless I divide it by another negative. Therefore, it will never work. And you may be asking yourselves, what if we put it to a negative base? Well, by the definition of a logarithmic function, our base has to be a positive number. Therefore, it's impossible for us to do this. This does not make a real answer, so no real solution. Now, there is a solution in the imaginary numbers if you want to explore that complex there. It's actually really interesting what the natural log of -1 is. It doesn't equal a real solution, but in the imaginary numbers, it's actually pi times I. And the reason why is that comes from this guy named Euler, and his equation basically says that e to the power of I pi is equal to -1. And you can explore kind of where that comes from. You see a lot in calculus where we relate it to trig functions and things like that. But that is ultimately what we're looking at there, that there's not a solution because I cannot divide a negative number and turn it into a positive. It's going to be imaginary if that's the case. And so that is kind of how those relate. That is how we can use those log and natural log buttons on our calculator. Remember that log is base 10 and that the natural log is log base E. So in the next video, we're going to talk about how we can solve logarithms if they're not in base 10, they're not in base E, and they don't divide pretty. What we can do and what are some different methods. And I'll give you a hint. What we're going to do is we're going to end up changing the base to something else so we can use these options in our calculator. So check out that next video on how we change the base to continue evaluating logarithms.